Great, thank you very much. I hope everyone can hear me, and I hope everyone can see the slides. So this is a preview of the Semantics 2 session happening this afternoon. So that's at 1645, Avenue 34, and these papers will be presented. I'll give a short overview in the rest of this talk. So what are semantic techniques? I guess being at POPL', everyone, I guess, has some familiarity with these. But I want to distinguish semantic techniques from kind of operational reasoning and things like that. So the goal is to understand programming languages by translating programs into mathematics. Or another way of putting that is, if we know the kind of mathematical domain that we're translating into, then in some sense we've found an invariant of all programs in some programming language. So we'll know something good about them. So a simple one is something like no programs go wrong, or something like that. And that's an invariant of all programs in that programming language. And semantic techniques have a kind of reputation for being a little bit esoteric, but there's been some enormous successes. So things like monads in semantics by Eugenio Moggi to try and tidy up the kind of mess that was semantics in the late 80s. And that got turned into monads in programming language design by Phil Wadler, and that's sort of taken over the Haskell world and beyond. Another example is effect handlers by Gordon Plotkin and Matteo Pretnar. This is started out as a way to try and understand what was going on with monads, and has turned out to be a massively useful sort of technique for modular effects in programming languages. And another success is expressive program logics. So once you get to program logics that can reason about concurrency and separation and things like that, then you need a kind of very solid understanding of what's going on underneath. And semantic techniques have been used in program logics like Iris. Now, I think the common thing between all the talks in this session is kind of heavy use of category theory in order to organize and explain what's going on. And for some people, category theory has a kind of weird reputation as some kind of esoteric thing that, you know, maybe I'll understand it one day, but I don't need to. I'm going to try and get you to understand a little bit of category theory here, because I think it's really cool. And the way in for me, when I first learned it, was not to worry too much about the mathematical background, which I didn't have, but try and think of rough analogies like types as the objects in a category, programs as morphisms, and then the composition rule is simply plugging in one program into another. And as a kind of sociological point, I would say that there are still some sort of holdouts in the community. So this is a quote from an old review I got some years ago, saying, side remark, basing abstract data types on set theory is more appealing to me, and I've always wondered why the community is so attached to category theory. Well, unfortunately for that anonymous reviewer, category theory is going nowhere away. No, it's going places, but it's here to stay in the community. So I want to give an overview of two techniques before I get into the papers, which come up in, I think, all of the talks. So one technique is ALGEBRAS. So it's one way to understand syntax via category theory. So if we have a signature of some kind of syntax, so we have negate, and I'm using kind of Prolog notation here, so negate is arity1 plus is arity2, and we have v many variables, varity0, and we can turn this into a functor. We can think of a functor as something that takes sets to sets as opposed to approximation. And so this gives us x plus x times x as x for negation, x times x for plus in variables. And then we can think of interpretations as morphisms. This is kind of the categorical idea. We kind of interpret things using the language of category theory, but trying to put things together. So here we're using the fact that functors are morphisms between categories, but then we have a morphism from that morphism into the identity one, and this is called an F algebra. So if you imagine this is sort of doing something a bit like data that you would give to a fold. And then we can define syntax as the initial or least F algebra. So a lot of the kind of principles in category theory are very general things like initiality, but they can be tied down to quite concrete things. Another technique is co-algebras. This is a way to understand behavior in category theory. We can think of outcomes as functors, so maybe finite non-determinism. We can think of like finite paraset, label transition systems, or stops, which stop is one, or we have a label goes to a new state. And then again, we model things as morphisms. Now, a system is a morphism. We take a state, we have some behavior, and then have a new state. And all possible behaviors form a final co-algebra. Okay, so that's some techniques from there. Let's look at the papers. So talk one is locally nameless sets by Andy Pitts. And the point of this talk is we want to represent syntax with binding. So binding adds a complication, right? Because there are many different ways of doing it. If we just use concrete names, as you might do on a paper representation, then you get into trouble with that your representation is not doesn't preserve alpha equivalence, and then you get into horrible things when you try and do substitution and things like that. And representing syntactic binding is important for mechanical formalization. If you want to formalize programming languages in a proof assistant, it's important for implementations. If you want to implement languages which have binding, and it's also important for mathematizing semantics, which I'll come back to in talk 3. And in this particular paper, Andy's looked at the locally nameless representations. This is one where we represent bound variables via De Bruijn indices, so that's we count the number of binders. We represent free variables, actual concrete names. And this has been a kind of very popular thing for both formalization and implementation because it's easier to reason about. And in the talk, he's going to define locally nameless sets. So that's a kind of generalization of a concrete data structure to just what does it mean for a collection of things to be locally nameless. And it turns out this supports a wide range of signatures, as we saw before, and so you can encode a wide range of syntaxes in this. And also, intriguingly, forms a known topos. So this is a kind of mathematical universe that we can kind of then talk about locally nameless things just as if they were just normal sets. And like the intriguing thing I think in this paper is it points towards a possible design of maybe a proof assistant where binding is built in instead of you having to redo it every time you want to do something. The second talk is about models of the lambda calculus. So here they're particularly interested in what are called graph models. This is where you interpret a function in the lambda calculus by its graph. So what does that mean? That means that you think about interpreting a function not as a mathematical function, but as a relation between finite multi-sets of observations on the input give some observation on the output. And this D is some domain that you're representing things in. And in the standard semantics like this kind of lives in the category of relations. Now, what they do in this paper is to generalize from the category of relations, which you can think of as like Boolean valued predicates on pairs, to thinking about a proof-relevant version. And this naturally fits into the world of sort of higher category theory, or bi-categories in this case. And to give you a flavor of what's going on, so you might wonder why a particular pair is in a relation. Well, one way of explaining that is a thing called an intersection type system. So these define rules for which elements appear in the relations. And intriguingly, each proof describes the potential behavior of the program you're interpreting. And so the idea in the paper is to categorify graph models, that is, to replace what was previously just a true-false thing with a whole kind of category of reasons why, to remember these proofs. And the consequences are that they're able to reconstruct approximating terms for individual behaviors. So if you have an individual behavior of that original program, you can find a kind of least term in some sense which has that behavior. And this enables them to give a very nice proof of characterization of the theory. So that's what lambda terms are equated. I'm going to finish soon. The final talk is towards a higher order mathematical operational semantics. So you may be familiar with the idea of small step or structural operational semantics, where we talk about, we define the semantics of a programming language or something like that in terms of the structure of its syntax. So here's maybe the semantics for a part of the semantics for a plus. If T1 reduces to T1 prime, then T1 plus T2 reduces to T1 prime plus T2. And one thing you can do with this is define programming equivalence as by simulation, right? So once you've got this kind of transition system structure, you can prove by simulation, you can construct by simulations. Now, our useful property we want to prove is called congruence. So this basically says if we know that the subterms are bisimilar to something else, then when we combine them, maybe as a bow tie operator, then the combined things are themselves bisimilar. So if two, and basically does bisimilarity is that preserved by all the constructs of the language, and this gives you a kind of compositional way of reasoning. And proving this by hand is extremely fiddly. And one way, and you have to sort of go through tedious kind of inductive proofs for all the different rules in your system. One way to not have to do this is to use rule formats, which basically say if your rules look like this, whatever this is, then you automatically get congruent. So a typical one is called guarded structural operational semantics. Now, back in the last millennium, Daniele Turi and Gordon Plotkin came up with a mathematical way of representing these rule systems, like this one up here, for first-order languages. And the contribution of this paper is to do this for higher-order languages. The complications here are that the labels you might put on these transition systems depend on the syntax of the language, which makes things a little bit more tricky. And going back to what I was saying earlier, the interesting thing about this operational semantics is there's an interplay between the algebras defining the syntax and the co-algebras defining the behaviors. And it's very, very sort of elegant and framework. Okay, that's everything I have. Thank you very much.